The broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, welcome back to Young Engineers of Today and NCSO, North Carolina Science Olympiad. Apologies for being a few minutes late. I ran into some technical difficulties with my Raspberry Pi, which is actually what we're going to be moving on to for the next couple of lessons, which are going to be the final couple of lessons. So it's going to be a bit of a change of tack from Scratch, but the reason why you guys spent time learning Scratch was because the Raspberry Pi utilizes Scratch as part of its learning programming. So we'll explore the Raspberry Pi today and Thursday and get as far as we can, and I believe that that'll put us right at the finish line there. So like I said, things are going to be a little bit different from here on out. No more Scratch on Scratch's website, but instead we're going to have a focus on the Raspberry Pi. So let's go ahead and get started. What is the Raspberry Pi, you might be saying? What does it do? What is it good for? Why would we want it? Well, those are all excellent questions. The Raspberry Pi, for those who are curious and don't already know, it is a fully functional $39 microcomputer. It also has GPIO pins that can control motors, lights, and sound or sense buttons, switches, or other environmental factors. That's an awkward sentence. So basically, it's a small computer. It's a really tiny computer, hence microcomputer. It has generally like a cell phone processor on it. Maybe a little bit more powerful than that. Pretty limited amount of memory, but you can hook a monitor and a mouse and a keyboard up to it and have it be a full-on computer to do computery things. So that's pretty neat. If you wanted to, you could have it, be a small, little, very limited home computer. You can use it for various projects. The fact that it's got a set of GPIO pins means that it's possible for you to be able to affect the sort of additional electronics with it. So you can hook it up to a small circuit of some sort, maybe something that controls a fan or something, or a siren, or a bunch of LEDs, or whatever the case may be. That's totally doable with the Pi. It uses a Linux operating system called Raspbian, which is based on Debian. Debian is just one of the billions of flavors of Linux. Linux in and of itself, pretty neato little thing. I don't know if you've ever heard of it. It's just a little thing. Linux is a well-known operating system, family of operating systems, and while its market share may not be as large as Windows or Macintosh, it's a very well-liked operating system for its customizability and its sort of its robustness and its ruggedness and things like that. But it's also notorious a lot of times for being difficult to set up because it is so customizable. Anyway, Debian is a particular flavor of Linux, and Raspbian is a particular flavor of Debian, which was meant to be as lightweight as possible and as easy to use for the Raspberry Pi. Here are a lot of the components, all of the components, in fact, pretty much all the components that make up the Raspberry Pi 3. The Raspberry Pi 3 has 4 USB ports. It has 1 Ethernet port. It has a composite video and audio output jack, so a 3.5 millimeter like headphone jack. It has a camera port, so you can plug a camera into it. It has an HDMI video output, so you can hook up a monitor or something using HDMI. It has a micro USB power input, so the Raspberry Pi is powered off of phone charger cables. So you know, if you've got a phone charger that uses a micro USB like an Android or something like that, you can use the same, or any small electronic really. You can use the same charging cable in order to power the Raspberry Pi. And on the 3, it can handle up to 2.5 amps. I don't know why there is this in the whoop. Oh, get out of here. There we go. It's got a DSI display port, a micro SD card slot, which is basically going to be your hard drive. It's got onboard Bluetooth as well as Wi-Fi, so you can wirelessly connect to your home network. And you can also wirelessly connect to different things. My Raspberry Pi, for instance, is a classic systems emulator. So I've got Bluetooth controllers that look like Super Nintendo controllers, and they're wireless. So I can plug in my Raspberry Pi near the TV, and I can sit down on the couch and boot up one of my controllers, and it'll connect to the Raspberry Pi, and then I'm off to the races. It's got a 40-pin extended GPIO, which I believe we get into what GPIO is later on. But GPIO, in case it doesn't, is general purpose input and output. And this is the best way for you to be able to have your Raspberry Pi sort of interface with the outside world, because then you can plug wires into it and hook them up to circuits on breadboards, or soldered circuits or something like that, and you can create all sorts of blinky lights and spinny things and moving things and stuff like that, all controlled by the Raspberry Pi. And then, since it's general purpose input and output as opposed to just general purpose output, you can have input. You can have buttons on those circuits that'll then send the signal to the Raspberry Pi. It can then process. You can have just a whole bunch of different stuff. Raspberry Pi's chip is a Broadcom BCM2837 64-bit quad-core CPU at 1.2 gigahertz with 1 gig of RAM. The RAM is, separated. That doesn't really necessarily mean a whole lot, but that's what it is. Did you raise your hand because you had a question, Micah? What's up? No, not necessarily. No, all good. It's not a problem that you have a Raspberry Pi 2. Yeah, that's the thing. Some of you might have a Raspberry Pi 2, might have a Raspberry Pi B, whatever. Doesn't really matter. Um, the important thing is that you've got a Raspberry Pi and you're able to interface with it. And no worries on the caps lock too. I've been there before. Um, but yeah, no. So the model of the Raspberry Pi, not not life or death. But yeah, Broadcom is the chip maker. Their chips are mainly used in the cell phone / tablet market. And then, yeah, GPIO, or general purpose input output pins, allow users to connect LEDs, motors, and sensors. That's the thing. I think the biggest difference between the 2 and the 3 is the power of the chip, the amount of power the micro USB can take, and the 2 does not have integrated Wi-Fi. You need to use a network cable in order to plug it into your network, which can be kind of a pain when you initially get it set up. But then you can get it set up on your network and then plug it anywhere that's convenient for you, and then remote into it with using your computer, which I'm about to do so that I can show you guys the interface and everything like that. 4 USB ports, network capabilities, modern audio video capabilities, 5-volt cell phone chargers, micro SD cards. So the micro SD card is the hard drive. The advantage being that you can swap them out and you can have different sort of operating well, different operating systems basically. I've got a friend who does the old video game systems thing like I do too, but then he's got a different SD card that just sort of has the plain flavor Debian on it, so that he can do more programming stuff and more home hobby projects. And all he has to do is just swap out the SD cards, and he's off to the races with a Pi that's got like kind of like a sandbox kind of a thing going on. So the in order to get started with the Raspberry Pi, it'll be good to have a Raspberry Pi, um, as well as an SD card with the Raspbian operating system on it, a 5-volt power supply. If you've got a 2, you will want something that I believe provides 1 amp. If you've got a 3, you can give it up to 2 amps. So just if you're not really sure, it's probably only sending 1 amp anyway, because I think a lot of phone chargers really only send 1 amp. Um, but you want to check the specs on the brick, the wall wart, whatever you want to call it, that big boxy thing that the USB cable plugs into, just to make sure. You've got an HDMI cable that connects the Pi to a monitor. You'll want to be able to connect the Pi to a monitor, and you'll want a keyboard and mouse because it is a computer. You need a keyboard and mouse for your regular computer, and that's how you're going to be able to control it, at least at first. Again, you can do some neat things like get it hooked up to the network, and so then instead of doing that, I can connect to it on my home network, and whoops, if I enter in the password correctly, I am in my Raspberry Pi. And I believe it still has VNC server. Yes, it does. So then I can pop into VNC and connect via remote desktop. 192.168. Good Lord. Oh dear. There we go. Continue. And there we go. Now I'm on my Raspberry Pi on my home computer. So this is the kind of thing you can do eventually, but at least at first you'll want to have it hooked up to a monitor and a keyboard and mouse and stuff like that, so you can control it in person. Oh, there's the Sabotage game, which you guys aren't really going to be able to do, but the idea is that everybody would move to the person's desk to their left who has a Raspberry Pi, and then they would unplug something, and the whole point is to figure out how exactly to get the Raspberry Pi up and running again. It's important because Raspberry Pis, when you're first getting them like started up and booted up and stuff like that, there's a very specific process that you need to do. You'll need to make sure that everything is plugged into the Raspberry Pi before you plug in power. You want to make sure that the SD card is in there. You want to make sure that the keyboard and mouse are plugged into the USB ports, and you want to make sure that the HDMI cable is plugged into the HDMI port and that the monitor is on before you plug in the power source. And the reason for that is because the Raspberry Pi tries to intelligently sort of guess how much power it's going to need, and it does that by polling all of the ports on it. If there's something plugged in there and it says, hey, I'm here, then it keeps that port on. If nothing responds, it turns that port off and does not listen to anything on it. So that is to say, if you had nothing plugged into the HDMI, as soon as you plugged in the Raspberry Pi, it would say, hey, anything on HDMI? No? Okay. And then it would turn off the HDMI. And then the HDMI would stay off. So you wouldn't be able to plug in a monitor and have the Raspberry Pi, recognize it and start sending picture out to it. You would need to plug in the HDMI and then unplug the power from the Raspberry Pi and plug it back in, basically power cycle it, and then it will go through the process again of checking all of the ports, and then it will see that there's an HDMI port there and that something's responding on it, and then it will start to send information out on it. So long story short, you want to make sure that everything else is plugged in before you plug in the power. And perhaps most infuriatingly, you want to make sure that the monitor is on, because that's not going to work if you don't. So then that brings us to the Raspberry Pi home screen. And as you can see, the Raspberry Pi is a pretty simplified little home screen here. They got a few different things. Got a nice little clock that's showing the wrong time. You're going to have some different stuff up here. You're not going to have like the Bluetooth or the VNC or the Wi-Fi indicator unless you're running a 3. However, you're going to have all this other stuff. So you've got your main Pi menu over here with a bunch of different stuff on it. You've got programming, Office, Internet, games, accessories, sounds and video, and system tools, as well as help preferences and so on and so forth. But good enough for us. We're going to check out what's in the programming one because we're going to be messing around with that stuff. So we got BlueJ, which is a Java IDE. So IDE is integrated development environment. So if you've ever messed around with programming, you know that, like with typing programming, not like Scratch, you'll know that not only do you need to type the code out, you need to have the computer interpret the code and tell you whether or not the code's correct, and then you need to have the computer run the code and turn it into a thing that you can run. And it's helpful also to have the computer let you know if you're running into bugs. And an IDE is sort of all of those things rolled into one. It's a text editor. It's a thing that allows you to build the code and run the code. It's a thing that tells you if you've got any bugs in your code. Just all sorts of things and stuff. Hence integrated development environment, because it's an environment for development where everything is sort of integrated into one thing. And you've got Genie, which is another IDE. You've got Greenfoot, which is another IDE. You've got Python 2 and 3, which are sort of like IDEs, kind of, sort of, kind of. You've got Scratch here, Scratch and Scratch 2. Then you got the SenseHat emulator. You might not have the SenseHat emulator. Sonic Pi, learn programming and computer science while creating music. Pretty neato. And the Tawny Python IDE, which is a Python IDE for beginners. And then you got Wolfram and Mathematica, which are math-based sort of tools, which are pretty neato. Wolfram Alpha, if you've ever checked it out, is a neat little thing. It's kind of like Google, except you can say amount of land each person in North America would get if divided equally. It might not be able to interpret this, but it'll try its best to. Let's see it do the computing. Okay, so it didn't quite do what we wanted it to do. Got close though. They figured out, hey, North American population, using closest Wolfram Alpha interpretation, land person in North America, as opposed to all those sea people we have to worry about. But yeah, North American population, 542 million people. Population, 542 million people. Population density is 57.2 people per mile squared, per square mile. So we kind of got an answer there, and that each person would have 157.2 of a square mile, sort of. Anyway, that's kind of the whole point of this. So amount of paper clips needed to reach the moon. I'm doing some pretty esoteric things as well. Wolfram Alpha generally does a lot better with actual mathematical stuff. Yeah, as you can see, it kind of flipped out. Well, anyway, but that's what it is. You've also got it on your Raspberry Pi. What we're going to focus on is we're going to focus on Scratch. So if you know Scratch 2.0, you can program Raspberry Pi Scratch, and if you know Raspberry Pi Scratch, you can program Scratch 2.0. So let's take a look at that stuff. Let me pull up the next presentation. All right, so here's the next presentation. So we may not touch on all this stuff today, but that's okay. We will not be continuing with Space Invaders, unfortunately. We're going to be moving on to a different thing from that. I know that's not ideal, but we want to make sure that we get everything done in time, because Thursday is actually going to be our last official meeting before you guys do NCSO, and that might change. We might have another, interim meeting or something like that. But as it stands right now, this is going to be it. So let's see how far we can get with this presentation today. All right, so let's review electronics. First off, we've got breadboards. So where are we reviewing electronics? Mainly because like I said, the Raspberry Pi has a set of GPIO pins. And those GPIO pins will allow you to connect wires to various electronics to do various electronic stuff. So if we want to learn how to do that, we're going to want to learn how to interface with electronics and how they work and stuff like that. So let's get started with the electronics side of things. First things first, we got breadboards. Breadboards are pretty neat little pieces of equipment. They allow you to quickly sort of build and prototype circuits and stuff like that for whatever you need them for, really. I mean, various purposes. It's kind of open-ended. I'm sorry I couldn't give a more useful answer than that, but the thing is there's so many things you can do with a breadboard that you can just say, hey, they're good for making stuff, and that kind of encompasses everything that they can do. But what exactly are breadboards? Well, so breadboards are just simply a piece of plastic and metal with a bunch of holes in it arranged in a grid. And the idea is you get these little wires with and electronics and stuff like that that have pokey metal end bits, and they plug into the holes on the breadboard. Pokey metal end bits is the official term, by the way. It's a technical one. And they basically you slot them in, and then they create a connection with the metal because the metal on the inside is conductive, and it allows you to hook up a bunch of circuits, or excuse me, components together into a complete circuit. Because the thing is, these bits of metal are all connected underneath the plastic. So if we were to look underneath, they would have these things here, and so they end up looking something like this. So if I plugged something into this bit right here, it would actually be connected to something over on this one because the electricity could travel along the metal here. Likewise, vertically, they're hooked up on the side, and we'll actually take a closer look at that on the next set of slides. So a breadboard is connected to itself on a lot of these, but not all of them. So in all of the middle ones, these two sets of columns in the middle, the breadboard is connected horizontally. That is to say, if you wanted to plug something, one second. If you wanted to plug something into here, it would be plugged into something in this one. Oops, let me make that a little bit clearer. So this one would be plugged into this one. So those two would be connected. Likewise, this one would be connected to this one. However, this one would not be connected to this one because there's a big break right here that breaks these two up. So these two are not connected, whereas these two are and these two are. Now these two are not connected to each other because the connection only goes horizontally in the middle. On the sides, however, they're connected vertically. So this one is connected to this one, and this one is connected to this one. Interestingly, though, along the sides, they're connected along the entire length. So that is to say, this one is connected to this one, and this one is connected to this one. So along the sides, they're connected vertically, and they're connected along the entire length. Along the middle, they're connected horizontally, and the middle, the very, very middle, the center, has a break that prevents the two middle halves from connecting to one another. If that seems a little weird or maybe confusing or anything like that, that'll make more sense. Messing around with breadboards, you'll be able to say, "Oh, okay, I get it now." You'll have a clearer idea of how exactly that works. So then, it's important to note that it is important to keep track of how components are plugged in to a breadboard. You might say, all right, these are cool because they're plugged in along the same, what's called a bus. So the horizontal ones in the middle and the vertical ones along the sides. A collection of holes that are connected to one another is referred to as a bus. So you might say, hey, okay, it's cool that these are plugged into the same bus because they're plugged into the same bus, right? But that would be not so great. You would actually not want them to be plugged into the same. You wouldn't want both ends of an electrical component to be plugged into the same bus. There's a reason for that. And that's because electricity is lazy. So let's say, if we go back up to this little drawing right here, let's say we plugged in a nice little LED here. Here's our LED, and it's plugged in to two parts of the bus, right? And it's in the same bus. The electricity travels along here. The electricity has two choices. Either it can continue to travel along the bus, or it can travel up the LED leg and into the LED, and then back out the other side. I'll tell you right now, it's always, always, always going to pick this one, because electricity is lazy. You see, there's this phrase that I'm sure you guys have heard before. Electricity takes the path of least resistance. Resistance is, you can think about it like electricity, like water flowing in a stream. And if the stream is nice, like if the stream bed is nice and smooth, and it's a nice wide stream, and the conditions are all good and stuff like that, the water is going to flow very easily. However, if there's a whole bunch of rocks and stuff, and the stream becomes very narrow because of blockages and things like that, the water is not going to flow as easily. A resistor kind of operates like a bunch of rocks in the stream. It keeps the electricity from flowing as easily. And electricity always wants to flow as easily as it can. So even an LED is going to have some resistance in it, just by virtue of the fact that it's built the way that it is. And so it will have more resistance than the bus, and the electricity will always want to travel along the bus. And then you get something called a short circuit. Short circuit is not great. Short circuit's called that because the electricity travels along a shorter circuit than the one you built, or intended to build. You accidentally built a shorter circuit, but you wanted it to go along the longer circuit. So the electricity takes the short part of the circuit, thus short circuit. Short circuits are at best an annoyance and at worst a fire hazard. So you want to make sure that you're avoiding short circuits as much as possible. In this particular situation, it's probably just going to be an annoyance more than anything else. But regardless, you want your circuit to do what you want it to do. So you don't want to plug it into the same bus because it's always going to travel down the bus instead of along the component because it's just going to take less work for the electricity to do that. Instead, what you want to do is you want to jump buses, like the Matrix, I guess. I don't know. Anyway, you want to jump buses. So as you can see, we've got two separate buses here, and the LED has one leg in each. And that's because the electricity will have no choice but to travel along the LED. If it wants to continue the circuit, it has to travel along it. So instead of the water having a choice of traveling along the nice flat stream bed or the rocky one, it has to travel through a rocky one in order to hit the nice flat stream bed again. So we want to make sure that whenever we're hooking up our breadboards, components onto our breadboards, that we're not hooking up both ends of the component, whatever electrical component we're hooking up. We're not hooking up both ends of the component into the same bus. Then you can see these concepts sort of put together in order to create a circuit. In this particular one, you've got electricity. Let's say electricity is traveling down this, and then it's going to hit this wire, and bam, it's going to hop onto this bus, and it's going to go, cool, I'm here now. Oh, hey, look, a resistor. But like, I can't go any further, so I have to travel along the resistor, and so it travels along the resistor, and now it's on this bus. And cool, there's an LED here, so I'm going to travel up the LED, back down the other end. Cool, now I'm on this bus. And then I'm going to hit this wire here, and now I'm here. So as you can see, there's a nice path that's traced from beginning to end through all these components because we jump buses. So I've been saying LEDs and resistors and stuff like that. Let's get ourselves a little bit more familiar with the actual electronics, those actual electronics. So LEDs. LED is short for light emitting diode, and I'm sure you guys have heard of LEDs in your life. Hey, have you guys heard of these things called light bulbs? But anyway, the point being, LEDs, that's what it stands for, light emitting diode. The reason why it's called that is because it is a diode, or another type of electrical component, that also just happens to emit light. And that's what a light emitting diode is a diode that emits light. Now, a diode, what's a diode, you might be saying? A diode is kind of like a one-way street for electricity. Always make sure that electricity flows in one direction and not the other, because that can happen with electricity. Streams tend to flow from the top of the mountain to the bottom. But imagine, if you will, this incredibly weird sort of situation in which instead of electricity, it's two ghosts and a laser. Instead of electricity flowing from the top of a mountain to the bottom, you had a half pipe, sort of, and water would travel down. But the problem is if the water traveled too fast, it would come up over here and it'd want to go back down this way again. And we wanted to ensure that water never traveled that way. It only traveled along the half pipe in this direction. That's kind of what a diode is meant to prevent. A diode is kind of like maybe like a door here that only lets water come in this way, but does not let water come back down. Now, as that door opened and closed, that door also happened to emit light. And thus you'd have this overused analogies analog for an LED. So an LED is a one-way street for electricity that also happens to emit light. It's important to note that you might go, hey, how does the LED know which direction is the correct direction? You know, how does the electricity know which direction is the correct direction? How does a diode determine that? And that would be a great question, because it is a great question. And the answer to that is that there's a very specific way that you can plug in an LED and have it be correct. There is a positive and a negative, and you always want to make sure that the positive and the negative are plugged in correctly. Imagine you were building a road just by taking other chunks of road and then just dropping them in. And you had one chunk of road that was a one-way street, and you plugged it in. You would want to make sure that that's oriented correctly. Maybe that's backwards. You want to make sure that that's not backwards. Same idea with an LED. You got an anode and a cathode, a positive and a negative leg. You always want to make sure that the anode and the cathode are plugged into the proper areas, and we'll go over that when we build the circuits and stuff like that. Next, you've got resistors. Resistors reduce the flow of electricity. They are the rocks in our stream. They make sure that electricity doesn't flow as freely, as quickly, as powerfully as it could otherwise. And this can be good because it prevents too much electricity from going through too quickly, and things like LEDs, can kind of pop open. They can get really hot, and then it can cause the air inside of the little plastic bit of the LED to expand so much that the plastic bit explodes. And thus you get little dramatic LED pops. So by putting in a resistor, you can keep the electricity from going through too quickly, from heating up too much, and consequently, you can keep delicate electronics from becoming too hot and doing something like breaking. Now, a resistor, resistance on the resistor is indicated by the color of the bands on it, because you could just print numbers on it. But a lot of resistors are very, very small, and it'd be very, very hard to read numbers. And resistors can all have very different values, so it's important to note that you might want a different resistor for the job. A resistor's resistance is measured in something called ohms, OHMS. And it's expressed as the Greek omega sign because it's cool. And the higher the number, the more a resistor resists. So a 330 ohm resistor is not going to resist as much as a 1500 ohm resistor or 1.5 kilo ohm resistor. So you always want to make sure that you got the right resistor for the job. And the best way to do that is to check out the colored bands on the resistor, because the colored bands will correspond to the resistance value. It's actually rapidly becoming a lost art, and reading those we can spend some time, going through the band coloration and stuff like that. But the thing is, it's becoming so much easier just to write apps and stuff like that that'll interpret it for you that it doesn't really matter. So the first circuit that we're going to be making with the Raspberry Pi, and if you don't have, like a breadboard and LEDs and stuff like that, that's okay. Just take a bunch of notes so that you know exactly what we're doing and why we're doing it. But the first circuit that you're going to be building is going to be a light, an LED, a resistor, and a battery. Are you asking what's the squiggly right here? Yeah, okay. So this right-hand side is sort of a simplified diagram of the circuit. We're not going to be like taking little thin bits of wire and tying them to the ends of the resistor and the LED like is suggested here. It's going to be plugged into a breadboard. However, that is sort of a visual representation of how the circuit might flow. But this isn't a very technical way to express that. The technical way to express that is actually with this diagram over here on the left. This is a schematic, and this is used by electrical engineers and electricians and stuff like that in order to determine how a circuit flows. And each of these weird little sort of bits on it represent a different components. And then simply the straight lines in between them tell you exactly how everything's supposed to be plugged in together. So if a straight line is here, it means that the two components are plugged in. This right here corresponds to the battery. That's what that means. That means direct current power, which usually is a battery. This one right here is the LED. And there are a couple of different ways that LEDs can be represented in schematics, but this is certainly one of the more common ones. And then finally, this right here is a resistor. This symbol represents the resistor. So by looking at this, we know, hey, okay, so an LED is plugged into power, and then a resistor is plugged into the LED, which is then plugged into power. Notice how this doesn't 100% line up with it because we don't have all of our wires at nice right angles and, not everything's oriented exactly perfectly. That's just because this is a diagram, an abstract representation of what a circuit's supposed to look like. It's not necessarily going to look like that when you're looking at it in your face. But yeah, schematics can get to be very, very useful because circuits themselves can get to be very, very complex. And so you'll begin to want something like a schematic in order to give you a nice abstract representation of how things are connected together. This is a pretty extreme example, but there are certainly more complex things out there. There are less complex things, but there are certainly more complex things out there as well. And so something like this becomes immensely useful because then you can go, okay, so let's go ahead and trace this wire right here. This is going to go here, near, near, near. All right, so it connects to a couple of other things. Let's keep going. Let's keep going. Connects to a couple of other things. Let's keep going. All right, so it hits this transistor here, and then it comes into pin 12 on IC302 MC14008 or 14008 BCP. Cool. By the way, I'm not going to ask you guys to interpret the circuit. This is something after you've become much more comfortable with circuits and you've been dealing with them for a few years. But yeah, so to answer your question and go a little bit down the rabbit hole, the squiggly line represents a resistor. As you can see, they got a couple of resistors here. R4, R3, R7, R8, R9. They got some capacitors, they got some diodes, some transistors, they've got grounds, and just all kinds of stuff. Integrated circuits, inductors, different kinds of capacitors. Anyway, point being, that's what the squiggly line is it means a resistor. Resistor. Oh, this is a CB radio. Oh, okay, cool. Yeah, sometimes they can get a little wild though. So this circuit would be plugged into the Raspberry Pi GPIO pins. Oh boy, 751. And that explanation alone. Okay, so when we say that the Raspberry Pi has GPIO pins, not all of them are necessarily going to be GPIO. That is to say, not all of them are going to necessarily be outputs, not all of them are necessarily going to be inputs, and not all of them are necessarily going to be general purpose. Some of them are going to have a very specific purpose. So the name, calling them GPIO pins, is a bit of a misnomer in that respect, but it's not 100% wrong either. As you can see, a lot of them are still actually general purpose. This is a map of what all of those pins do on the Raspberry Pi because they all have their own function. Anything that's orange and is labeled with GPIO 2 or 3 or 4 or whatever is going to be a general purpose input-output pin. Anything that's labeled GND and is black is going to be a ground pin. Just as you need power, you also need ground. Ground gives a direction for the electricity to flow from the power. And you need to complete a circuit in order for the electricity to be able to flow. The electricity is not going to flow unless it hits a ground somewhere. Then you've got up there on the upper right-hand side, you've got 5V PWR in red. That is short for 5-volt power. 5-volt power allows you to send power out of the Raspberry Pi into your circuit. 5 volts of it, to be exact. It pretty much says what's on the tin. It sends 5 volts of power out. So you got 2 pins reserved for that. Then you got 3.3 volts power, which is the 3.3 VPWR in yellow. It's pretty hard to read. It's yellow and it's got the white writing, but pin 1 and pin 17 are going to be 3.3 volt power. So same deal as the 5 volt power, except instead of sending out 5 volts, you're going to be sending out 3.3 volts. Then you got a couple of pins labeled reserved, which are going to be strictly for Raspberry Pi stuff. And then you've also got UART0TX and UART0RX. These are transmission and receiving pins, which allow you to send and receive information on those pins using the UART0 protocol. So you can send data in and out on those pins. To another thing, like maybe a small Arduino or something like that, whatever the case may be, or an LCD or something. Point being, you'd be able to transmit information on those pins to a circuit that has maybe some logic components to it. So I wanted to touch on those pins before we got done with class today. Thursday, we're going to spend that time hooking up the circuit and getting the Raspberry Pi to talk to the circuit so that you can understand exactly how something like that sort of interacts on both levels, both the hardware and the software level. And that's going to be our goal for Thursday. We're going to get through that, and hopefully we'll get through it pretty quickly so I can leave some more time for question and answers for you guys. For now, though, let's do the poll questions, and then we'll leave it open for question and answer time right now. I've got to pop off at 7:58, 7:59 because I've got one more class tonight at 8 o'clock, and I want to make sure that we're able to get through their lesson as well. So I'm going to go ahead and end the recording and do the poll questions, and